Hello everyone, I'm Hiroki Kechi from NTT. I'm very pleased to have this opportunity to talk to you. Today, I will present a new framework for automatic failure recovery in ICT systems by deep reinforcement learning. Here is the outline of my talk. First, I'll start by the introduction and background of failure handling. Then I'll explain our idea and proposed framework and show you some experimental results. Finally, I will conclude my talk. Now let's begin. Failure handling of ICT system is a crucial task for system operators. Failure handling consists of several phases. Especially, it takes a lot of time to identify the root cause of failures and decide what recovery action should be taken. The speed up of this phase is crucially important to maintain service quality and system reliability high. In failure handling, metrics and logs generated from the system are very informative and usually collected by data management systems. In order to speed up the failure handling and minimize impact on customers, automatic recovery has been expected. Recently, automatic execution of recovery actions has become possible by using automation tools such as runbook automation. To automate the recovery process, we need to define rules associating the metrics and logs with corresponding action workflows in advance. By predefining such rules, if a new failure occurs and some metrics and logs are obtained, the associated recovery action workflow can be executed automatically. This approach seems promising, but in practice, the rules between metrics and logs need to be created manually, and this is a tremendously difficult problem. In general, there are many monitoring items, and the observed metrics and logs are non-deterministic and randomly fluctuated. Plus, constructing complex action workflows from scratch for each type of failures is very time-consuming. Moreover, for some failures, there is not sufficient knowledge of recovery. For frequent failures, historical record of failures, such as trouble tickets, are accumulated, but for rare or unknown failures, there is no such thing. So, constructing workflows for such unknown failures are very difficult, and supervised learning relying on the existence of failure data cannot be used. Taking such problems into account, we set these two objectives. First, we aim at automating the construction of auto-recovery mechanisms. In other words, we want to create automatic recovery workflow without human intervention. Second, we aim at handling various possible failures, including rare or unknown failures. In this work, we tackle these challenging tasks based on these two ideas: deep reinforcement learning and chaos engineering. From now on, I will explain these two concepts briefly. First, I will describe deep reinforcement learning. A simple reinforcement learning is, as you know, a machine learning framework for learning a policy for an agent taking the optimal actions under a given environment to maximize cumulative rewards. For example, we consider agent and a certain environment. When this agent takes some action, the environment changes its state, and the agent observes the new state and the reward. The reward is a function indicating how good the action the agent took was to achieve the goal. The agent determines the next action based on the observed state according to what is called a policy. The agent also updates the policy based on the given reward. By repeating this procedure, the agent finally obtains the optimal policy, which tells us the best actions under the observed state. As an algorithm of reinforcement learning, Q-learning is often used. In Q-learning, The agent updates what is called the queue function so as to minimize the dot function written in the lower part of this slide. But an original queue function can only take a discrete dimensional state as an input. By approximating queue function by deep neural network, we can handle the situation where the state is continuous and multidimensional. We call such a neural network deep queue network. Of course, what I told now is one of the basic idea of deep reinforcement learning, so there are many further improved methods recently. Deep reinforcement learning have been applied to various areas and provided superhuman performance in some fields, such as Atari video games, chess, or other board games. In addition, deep reinforcement learning can be considered as a promising method of automating various tasks in the real world, such as autonomous driving. So, in this work, we explore the possibility of utilizing deep reinforcement learning in automatic recovery. Next, I will explain the other important concept, chaos engineering. This is a type of evacuation drill for systems conducted by injecting failures. In chaos engineering, considering that the system will definitely fail sometime, we intentionally inject various types of failures and collect failure data. By understanding the system behavior and analyzing failure data proactively, we can prepare countermeasures for possible future real failures. It is true that the conventional fault injection is also aimed at understanding failure impacts and thinking about their solutions by injecting possible known failures. But compared to such conventional fault injection, in chaos engineering, we perform rather random, extensive, and iterative failure injection. So, we can expect that the chaos engineering reveals the characteristics of unknown failures as well as known failures. Recently, many chaos engineering tools have been developed, and we can use them easily. Taking these two concepts into account, let's move on to the explanation of our idea. Our idea is very simple. Now, let's suppose that we have a verification system imitating the certain product system. Once we obtain an optimal recovery policy in this verification system, we can apply it to the product system. So, we aim at constructing the recovery policy of this verification system. First, we inject some failures into this system by using chaos tool like this. Depending on the types of failures, we can collect different failure data. Using these data, we train the DRL agent. The DRL agent may take actions by trial and error at the beginning, but by repeating this procedure, we expect that the DRL agent finally acquires the optimal policy for recovering from various types of failures, including those which have not occurred in real operations. Now, I will explain our proposed framework in detail. As I already told, we have the DRL agent and environment, including the target system, chaos tools, and other items. The agent and environment interact, and the recovery policy is autonomously constructed in accordance with the following steps. The first step is failure injection. Certain failures are injected into the target system using chaos tools. The chaos tools that can inject a wide variety of failures are desirable. The second step is observation of state S. The agent collects data such as metrics or logs generated from the target system within a certain time window and converts them into a numerical vector, that is, preprocessing. We cannot directly observe or define the status of the complex target system, So we instead consider such a numerical vector as a state S. This state S is generally a continuous and high-dimensional vector. The next is determination of action A. On the basis of the observed state S, the DRL agent calculates Q function Q of SA, and the agent determines which action A should be taken in accordance with the current policy. Then, the agent executes the chosen action in the target system in the next step. In practice, the system status changes after this step, and it may take some time before the convergence of the status. For example, instance reboot or network routing takes some time until the state converges. So, it is better to keep from proceeding to the next step for a short time, depending on the target system. After that, in the next step, the health checker monitors the status of the system, and depending on its result, the agent receives a reward R. We set the reward function to minimize the number of recovery actions. For example, if the target system is in a normal state or in a state closer to the original state than before, the agent receives some positive R. Otherwise, the agent receives no reward or penalty or negative reward. And then the agent observes the new state as prime. The agent again collects data from the target system and constructs a numerical vector, namely a new state as prime. In the next step, the agent updates the deep Q network DQN. The agent accumulates the tuple S, A, R, and S prime in the memory and updates the DQN by randomly picking up stored experiences, namely performs what is called experience display. On the other hand, in the environment, we judge the end of the episode. If the target system turns out to be recovered, the current episode is finished, and the next episode starts from the first step. If the target system is still in failure, the agent iterates the procedure from the third step, the determination of the next action based on the new state is prime. However, if the number of executed actions exceeds the predefined threshold, we interrupt the current episode, restore the target system into the original state by using restoration tools, and start a new episode from the first step. Finally, we judge the convergence of training. After convergence of learning, which is defined as, for example, the averaged total reward over several successive episodes exceeds a certain threshold, we finally obtain the recovery policy. Now, let's move on to the explanation of experiments. We conducted a simple experiment to evaluate the feasibility and effectiveness of our framework. We built an environment composed of multiple containers and considered the problem of learning the optimal policy. The system size is small, but our setting has these essential complexities also found in a real environment. The space of possible observations is large because the amount of traffic randomly fluctuates and the status of load balancing changes the trend in traffic. Moreover, the policy to be learned will be complicated because the chaos tool injects many failures, specifically 12 combinations of failure types and locations, and their simultaneous occurrence. And we consider the problem of learning the policy that makes the total number of actions minimal. This is the detailed setup of our environment. We built a Quantus version 1.16 cluster on a physical node with Ubuntu 18.04. For the target system of our experiment, we created a three-tiered web architecture model consisting of two Nginx containers, two Redis containers, and two MySQL containers. Each container is deployed in a separated pod. The traffic flowing into Nginx and the traffic flowing between Rails and MySQL are load balanced between two distinct containers. For our chaos tool, we created a Pamba pod, which enabled us to inject various types of headers such as traffic delay and packet loss. We assume that the same types of failures can occur at most two locations. So in total, there are 42 patterns of failures. Next, to emulate realistic background traffic, we sent HTTP requests to the target system by using Locast, a load test tool. We created a Prometheus pod to collect system metrics such as the amount of inbound-outbound traffic at each container. We stopped the self-healing functions of Kubernetes because we need to keep containers from restarting automatically in the middle of reinforcement learning. Then, here's the setup of deep reinforcement learning. We implemented double deep Q-learning, which is one of the methods of deep Q-learning. State S was a 24-dimensional vector whose elements were the normalized values of system metrics collected with Prometheus. System metrics were defined with not the instantaneous values, but the cumulative values during 45 seconds so as to alleviate the effect of fluctuation. The action space includes 6 actions, each of which corresponds to each container's restart caused by the successful execution of the deletion command and recreation command. In this experiment, the restart of container can recover from any of delay and packet loss. The reward was defined like this. If the agent takes necessary and sufficient actions to recover from failures, it receives a total reward of +1 or a penalty otherwise. This definition of reward is intended to minimize the number of actions executed for recovery. We finished one episode if all failed containers were recovered. We iterated episodes until judging that the training was converged. Here is the result of the experiment. This figure shows the obtained reward averaged over the last 10 episodes with a blue curve. The red dotted line indicates the criterion of convergence of training, 0.95. As you can see, the training successfully converged after 732 episodes. The elapsed time was about 58.5 hours, and time per episode was about 4.8 minutes. We can see that the reward after the 732nd episode almost always remained above 0.9. This means that the learned recovery policy can correctly identify failed containers and recover the system by the minimum number of actions with high probability. So, our framework worked well online and the recovery policy was able to be successfully obtained in this small system. This implies that it is possible for small ICT systems to autonomously acquire self-healing functions without any detailed manual design based on technical knowledge of operation. But from a practical viewpoint, we need to discuss the scalability of this framework. If we apply this framework to larger systems, we need to take measures to shorten the training time. So let's investigate the training time in a little more detail. The time for one episode can be roughly divided into three types of times. Time for restoration of the system, TR, time for action, TA, which means the container restarting, and time for fetching the system metrics from Prometheus, TM. The TA and TM need to be repeated several times until recovery. What is important is that these three types of times are determined by the system, and they are difficult to shorten. On the other hand, the total number of episodes and the iteration per episode (NA) could be decreased by developing another DR algorithm. This is one possible way to shorten the training time. As another possible way to shorten the training time, if the system is large, we can reduce the dimension of the state and action spaces to as small a number as those in our experiment. This is possible by dividing the whole system into several partial systems and applying the proposed framework to each of them. Multi-agent or hierarchical reinforcement learning may also be promising. Further evaluation of the scalability of our framework is a significant future work. Here is the conclusion of my talk. First, I explained the difficulties of automatic recovery, and then I introduced two concepts: deep reinforcement learning and chaos engineering. Then, I described our proposed framework. I explained the experiment in a Kubernetes-based container system and evaluating the training time. We have a lot of future work. To name a few, from the perspective of quantitative variation of performance, we need to conduct further experiments for various situations and platforms. The scalability is one of the most important topics in this framework. And finally, in practice, other factors may be considered as rewards or penalties, such as safety, workload, or energy consumption. This is the end of my presentation. Thank you for listening.